All right, so what we talked about in the previous two videos, we talked about that we have three types of two-dimensional motion or two-dimensional projectile motion. One was when it was initially pointed along the x direction with no angle of launch. So technically theta is 0, okay, and the velocity, the initial velocity is just v0. And the second type was we give it a little bit of a initial angle, or initially it was pointed towards this point at angle of theta, which is non-zero, okay? And we have two very important points in this second type is the maximum point, point H, and a range point, point R, right there, okay? And these are the equations that we talked about it. The third type was if it was launched below 0. So the only difference from third and the second one is that in order to solve the equations for the third type, you have to have a negative theta. So for example, if you have a tan of theta here, you have to have a tan of negative theta. So the only difference was that you're dealing with a negative angle, okay? And for the second and the third type, we said that we have a very important, for the second type, in fact, not the third type. For the second type, we said that we have a two very important points. This point, which is point H, or the maximum point, and point R. And point H is a point where the maximum height will happen, okay? At this point, we have the same type of velocity along the x direction, no matter where you're at. The velocity along the x direction will always stay the same because it's a constant velocity motion. Along y direction, it's just a free fall, a freely falling object only due to gravity, no air resistance. So it's a free fall, okay? So at that point, the point H, the velocity along the x direction is constant, okay, as you can see right there in my cursor. Look at this, all right? And then velocity in y direction at that point is 0. And I explicitly talk about each point. For maximum point or point H, we have these type of formulas. Velocity is constant along x direction, velocity in y direction is 0. Height of that point is this, v initial vy squared over 2g. And we have a t of h time to get to that point, just using the simple constant acceleration formulas, okay? And this has to be here. So time to get to that point is this. And for the range, we have, which is right there at that point, which is the opposite side of the launch point, okay? We have the t of r. To get to that point, it is the double of the t of h, or double of this value right there, 2 times the initial velocity sine of alpha over g. Now, since it is a motion with constant velocity and along x direction, I can just write it like that. So r is v of x tr. V of x is constant, v naught cosine alpha, times the tr, which is 2v0 sine alpha over g. And then you have this value, and you can represent and show that value like this, because 2 sine cosine is just sine double, or sine 2 alpha. Now v is squared right there over g. All right, so we talked about it. Let's actually get to solve some examples here. So example number 1, a falling care package, 0 launch angle. So an airplane is moving horizontally with a constant velocity of plus 115 meters per second at a magnitude of 1,050 meters above the ground. Determine the time required for the package to hit the ground, okay? Now, this third part of the video is mostly problem solving, okay? So this will be an example type of video. So I want you to pause the video right now, write down what you have, okay? And try to solve the problem. You have to have a paper and a pen with you. And once I start solving the problem, you have to solve it with me at the same time, and solve it a couple of times after me, okay? So let's take a look. We have an airplane moving in that direction with a speed of 115. meters per second plus 115. So that means that we have some sort of a coordinate system. So I have to draw a coordinate system right here. So let's draw a coordinate system. So let's see, I have X right there, and I have Y in that direction. So kind of like this. Okay, so I have X right here. Okay, and I have Y right there. Okay. Okay, so X is that direction, Y is that direction, and it is moving with a positive 115 meters per second along the X direction. Remember, this is going to be freely falling along Y, and it does not have any initial speed along Y direction. It's just falling down. So what I have here is that this package is exactly the same as if it was freely falling. So the time that is required for this package to get to the ground will be just the same time as if it was just falling down from the sky, freely falling. So they will have the same timing. If you want to know what I'm talking about, remember this. Okay, at time equals 0, the freely falling object, which is the red ball here, will be in the exact same position vertically or along Y direction as a object that is being pushed or moving in two directions, both X and Y. So along Y, we can find the time. Okay, so the time is the time that it requires to come to ground with some sort of a initial position, which is at this point is this much, 1,050 meters above the ground. So we know that X is, or in this case, it is Y, in fact. So we know Y is half AT squared plus V0t, right? And this is along the Y direction. And along the Y direction, we are dealing with a free fall. We are dealing with a constant acceleration of G, which is downward all the time. So I know that G is always down, okay, which is negative 9.81 meters per second square, okay? So we know that. And now let's put everything here. Initial velocity along the Y direction is 0 because it was just horizontally, not vertically, pushed from the airplane. So this guy is 0. What I'm dealing with is this Y, which is 1,050 meters above, equals half G is 9.81, right? So 9.81. And if I want to write it more clearly, I have to write it like this. So let me get rid of this for a second. If I want to write it more clearly, this is delta y, change of the height, right? Or the displacement is that. And change of height. So once it's getting to the ground, so it is y final minus y initial equals half a is g t squared, okay? So y final is 0 because it is at the ground, okay? And y initial is 1,050 meters above, half g is negative 9.81 t squared, okay? So you have negative 1,550 meters above. You have negative 9.81 over 2 times t squared, okay? So this negative and this negative will go away. Okay, in order to find t is 2 times 1050. So 2 times 1050 over 9.81. And it is t squared, but right now we're dealing with t, so I have to put everything under the square root. Okay, so that will be your t. Put in the calculator to see what this is. Whatever the number is, it will be in seconds. Okay, it will be in the unit of seconds. So that's what the question was asking for. Determine the time required for the package to hit the ground, and that's what we found actually. See, I didn't even care about this 115 meters per second for this problem, because literally it's just the same as if you're somebody's up there and dropping the package down. It'll take the same timing. Okay, it'll take this much of time for the package to hit the ground, just like as if it was just freely falling down from the airplane. Okay. Okay, so I ended up putting this in the calculator, and I got 16.3 seconds for the time that that package will take to hit the ground. Okay, so now let's go to exercise 2, the velocity of the care package. What are the magnitude and direction of the final velocity of the care package? So where does the package land? So these two are the two questions that we have, but we have all the equations right here. We have everything that we want right here in front of us, okay? So that's what we're dealing with at the moment. All right, so I encourage you to think about this question, write down what you have one more time, try to put these equations in place and try to solve it. And have a pen and a paper in front of you. Work with me as I'm solving this problem, all right? Okay, so now what we have is we're looking for the final velocity of the care package, okay? That's what we're looking for. Now remember, it does not say the velocity along x or velocity along y. It's caring for the final velocity. It's looking for this guy, v, okay? So that's what we were looking for. V is what we were looking for. And we're looking for this distance as well. We're looking for, let's just call it x. The location of the care package that it's going to land, okay? So along the x direction, the velocity is always constant, okay? Along the x direction, we have a constant velocity right there. And it is always the initial velocity because it does not change. We have no air resistance. It will still be the same. So it will be 115 meters per second along the x direction here, 115 meters per second along the x direction here, and same over there. So it is 115 meters per second. Along the y direction, I can figure it out because we have a motion with constant acceleration along the y direction, and I can use the constant acceleration formulas to find the velocity. So you remember this? Velocity if of at plus v0, it's along y, okay? Initially, it was launched with 0 velocity along y direction. And I know a is just, this a is just negative g, right? So what I can write is this is negative g times t. And negative g is negative 9.81. T was what, 14 or 16, something like that, as I just calculated a few seconds ago. Right there, 16.3. So I have 16.3 seconds for my time, right? So if I multiply these two with one another, let me actually real quick calculate it to see what I can get. I have 9.81 times 16.3. It is giving me about close to, so negative 160 meters per second. And that's what it gave me. So along the y direction, we have that. And along the x direction, we have that. But we're not, the problem is not asking for along the y or x. It's asking for v. But something that we know from our vector analysis that these two vectors are making a triangle, right? So I have a vector v of x along x direction. I have v of y along y direction, and I can easily find their product, or v, because this is a right triangle. This is a 90 degrees triangle. So the velocity then, the final velocity then is square root of v of x squared plus v of y squared, which is v of x is 115 squared plus v of y to the power of 2, and v of y to the power of 2 is negative 160 to the power of 2. They are both under the square root. Let me get rid of this little tiny area. So just making sure that everything is under the square root, okay? And this will be your final velocity, the magnitude of your final velocity, okay? Now it's asking, where does the package land? Super easy. We want to know how far it will go along the x direction. So we know the time for that, the time for the motion. So this is part B, right? So we know that t, or the time, is 16.3 seconds, okay? And we know the initial velocity along the x direction is constant. I can't emphasize more than this, is constant. All right? So meaning that in order to find x, I can just use a constant velocity formulas. X equals vt, right? X is velocity along the x direction, which is 115 times t, which is 16.3. If you calculate your x, then it will be 16.3 times 115 meters per second. Let me calculate it one more time. So 115 meters per second times 16.3 is 1,874.5 meters. Okay, and I can just write it like this. I can just write it as 1.8745 kilometers. And that's my final x. I'll put it in the box to make it clear. Okay? So we oftentimes think that we don't have air resistance, but in reality, when we are on Earth, we are dealing with air resistance. We can't just neglect the air resistance, right? So if we consider the air resistance, and it is not for this course, but I'm just telling you because it's the information has been provided in the book. So and a lot of physics students on a higher level, when they're taking mechanics, they're dealing with these type of problems. But for this course, you're not. So, but when we have an air resistance, calculations becomes way more complicated. And then accelerations is not constant anymore because we have an air resistance that is pushing it backwards. And the effective air resistance can actually be large. It could be large enough to overcome the effect of gravity and acceleration due to gravity, and eventually along the y direction we'll have a motion with constant speed or constant acceleration. And the maximum height and range can change. So in other words, rather than ending up here, I have ended up right there. Rather than ending up in a range of higher position, I have ended up right there, okay, because of the air resistance. Air resistance is killing and turning everything to friction, turning everything to heat, because it is some sort of a resistance, right? And the trajectory is no longer symmetrical. Okay, it's not like a pink that you can see is symmetrical. It is some sort of a asymmetrical shape. Okay, so let's take a look at this example. The projectile is launched at a 30-degree angle above the horizontal. Ignore air resistance. Okay, that's what I'm going to do. Even if you don't tell me, I am going to ignore the air resistance for this course. The projectile's acceleration is greatest. The projectile's acceleration is greatest at point between the launch point and the high point of the trajectory, B at the high point of the trajectory, C at a point between the high point of the trajectory and where it hits the ground or the range. And D, it is a misleading question. The acceleration is the same but non-zero at all the points along the trajectory. Yes, that's the answer, because the acceleration is the gravitational acceleration due to the gravity. The object is freely falling in y direction. Okay, remember the x and y, the motion along the x and the motion along the y directions are they are independent. Okay, they don't affect one another. In y direction, we always have free fall. In y direction, in y direction, we always have free fall. But in x direction, we have in x direction, we have velocity being constant. So we have a constant velocity type of thing. All right, so just have that in mind as well. It is very important. Okay, so along the y direction, we have a free fall. Along the x direction, we have a constant velocity motion. So if you have a free fall, the acceleration will always be the same. Okay, it does not matter where you're at. It will always be the same. Take a look at this, for example. If you remember this, the free fall, the acceleration does not depend on each point. It's always towards the Earth's center. It's negative g, or negative 9.81 meters per second square. It does not depend on the points. Okay, so maximum range of the projectile. What initial angle will give the maximum range of the projectile? Okay, now in other words, if I have y direction right there, and if I have x direction right there, and if I have a ball or an object which is going to be launched at an angle of theta v0, okay, we want to know what angle will give us the maximum range. That's what we wanted to know. So the maximum range will happen at what angle? And they did some experiment, and they ended up, going all the way from 1 to all the way to like 90 degrees to see what angle will give us the maximum range, and it happened to be a 45-degree angle. So a 45-degree launch angle gives the greatest range. Other angles falls shorter. So this pinkish color that you see here, not pinkish, it's purple actually. This purple color that you see here will give you, with an angle of 45 degrees, will give you the maximum range. So meaning this range along the x direction will be maximum for this ball. Okay. All right. So the height of the kickoff. So we have another example. So a place kicker kicks a football at an angle of theta and an initial speed of v0. Ignoring air resistance, determine the maximum height that the ball can go in terms of v0, g, and theta. And we have done it before. So I am just going to show you where I have done that. So if you are looking at this, let me go all the way back. Yes, so for maximum point, or h, the velocity along the y is 0. The velocity along the x is constant, which is whatever it was before. It will be the same, which is right there, as you can see. That point of h is having a height of this much. So v0y squared over 2g. So in other words, this is just a time-independent formula. So delta y is what we're looking for. Okay, we want to see how far it's traveling from 0 all the way to that height, or h. Okay, that's what we're dealing with. So we have v final along the y squared minus v initial along the y squared equals 2g delta y, negative 2g delta y, right? So finally, when it gets to that point along the y direction, it will stop. So this guy is 0, okay? Initially, it was v0y, okay, or initial y, or then what we have is v0 sine of theta, okay, squared equals negative 2g, and delta y is just that, the height of that point, because it starts from 0, go to that point, which is h. So, which I'm just going to call it h. And now this negative and this negative will cancel out. And then what you have is h, or the height of that point, being equals to v0 squared sine squared theta over 2g. And that's the height of that point. I have the same equation right there. You can take a look if you want. Right there. Right here. So v0 squared sine squared over 2g. It's the same here as well. Okay. So hang time. Now, when this player kicks the football at an angle of theta and initial speed of the ball was v0, again, we ignore the air resistance. We want to determine time for the ball that is in the air. So the time that it requires for the ball to go from this point all the way to this point and then coming back down here. So we know that we have a symmetric type of motion, right? We know that the time that it will take for the ball to get to this point, to this height, is t of h, okay? And it will take the same amount of time for the ball to get down here, so it will be another t of h. In other words, in order to find the time that it requires for the ball to start from there and go all the way up and then coming back down is just the time of the range point, or it is double of the time of the height, or the maximum height point, or point h, okay? It is actually h, not a. It looks like a, but it's h, okay? So, and So what we have is 2 times the time that it requires for this object to get to the top. So we have it right here. The time is v0 over g, or v0 sine alpha over g. So 2 times v0 sine alpha, which is in this case is theta, over g. Okay. So by the way, these two are the same. These two are the same. Now, we talked about range before, but we're going to go over it one more time here. Range is the horizontal distance the projectile travels before landing, okay? In other words, it is the opposite side or in the opposite direction, an opposite end of the trajectory along the x direction, or r is xf minus x0. Do not memorize the range equation, and that's the range equation, but don't memorize it necessarily. I mean, you can memorize it, put it in front of the bridge, or, where you put your photos or family photos and memorize it, v squared over g sine 2 alpha. And I over years of teaching this, I have it in my mind, but I mean, you don't necessarily want to remember that. The range can always be determined using the previous kinematic equations. That is very true. And on an exam, if you start with the range equation, it will be marking correct, because I want you to be able to use the kinematic equations, just like what I did. Take a look. So what I did here, for the range, okay, I said the v of range along the x direction will be just initial velocity. So the v of range is just initial, whatever it was, it is the same. And the time to get to that range is the time, double of the time to get to the maximum point. And in order to find the range equation, okay, in order to find that, it is the constant velocity along the x, right? We have a constant motion with a constant velocity. X equals vt. V of x is v0 cosine, and t is just 2v0 sine over g. Okay, it's the same that I found right there. And then you can write down that very easily. Okay, so don't memorize it, because you can drive it, and you can always have your equation sheet with you, the one that I have provided for you. Okay, so now, so the time it takes the object to reach its highest point is half of the time it takes it to return to the same point. One more time, the time it takes the object to reach its highest point is half the time it takes for the object to return to the same point. In other words, this point requires it to double time. For example, if it takes 3 seconds for the ball to get to this point right there on the top, it'll take another 3 seconds to get down. In other words, you need 6 seconds to get down here, okay? And the velocity at the same two vertical points has the same magnitude, and that is something that we have seen it before. It is right here. So at the same height, for example, these 2 points have the same height. This point and this point, they have the same height. They have the same magnitude for velocity. However, the velocity on one of them is negative, because this negative means that it is along the negative direction, okay? By concept, we don't have a negative velocity. The negative in front of a number means that it is along the negative direction. So one direction is positive, one direction is negative. You want to know which one we're talking about? That's why we put a negative behind v, okay? So negative velocity means it's in negative direction. We already talked about it in the first part of the video. Okay, projectile motion. Now, pause the video for a second, read this problem, write down what you have, and then let's work on it together. Okay, so suppose a marble is launched horizontally, so kind of like this, horizontally. With an initial speed of 3.56 meters per second, it hits the ground. So the time it'll required for this object to come down all the way to the ground, and let's say that this is my ground. Okay, this is the ground. The time it requires for this to happen is only 0.682 seconds, not even a second, less than that. Oh, it's actually the distance. So it's going with that velocity, okay? It is going with a velocity of positive, it doesn't look like negative here, and it hits the ground 0.682 meters away from the launch point. Okay, so if this is the launching point, I have this to be 0.682 meters away from the launch point. How long is it in the air, and from what height was it launched? So we're dealing with a motion and constant acceleration. Motion and constant acceleration along y, it is always g and it's always down. So negative g is always down. And with the constant velocity along the x direction, correct? So I can easily calculate that. I have x equals vt, okay? X is 0.682. V along the x direction will always be constant, so 3.56, and I can find the time, okay? How long is it in the air? So I can find the time. It's asking to find the time. So time is then 0.682 over 3.56. Whatever it is in terms of seconds. Now, from what height was it launched? I can easily find that as well. I know that along the y direction, we have a motion with constant acceleration. So along the y direction, we have delta y equals negative half gt squared plus v0t along the y direction. Okay, I know that initially it had no velocity along y. Okay, delta y is what we are actually looking for, because initially it is y final minus y initial equals half gt squared, right? So initially it was at some point that we were looking for, but finally get to the ground and it ended up being at 0. So what I have is negative y initial equals negative g, which is 9.81 times t squared, and that is the t that I am dealing with. So t squared, and I am just going to use this t and bring it down here. Okay, so this negative and this negative will cancel out. I have my height of that point, or y of initial, being half 9.81. T was 0.682 over 356 squared. So that is the final answer. That is the height. Okay. So another example, a rock is projected upward at an angle of plus 73 degrees north of east from the edge of the ball of a tall building. So we're going to write down everything that we have at the same time that we are going. So this will be 73 degrees. The rock reached its maximum height above the building 1.25 seconds after being launched. So the time to get to the maximum point, or point H, is 1.25 seconds. Okay. The rock struck the ground 6.13 seconds after it was launched. So time to get to ground is 6.13 seconds. Assume there's no air resistance. Obviously, there's no air resistance. Now, we're looking for what maximum height above the top of the building is achieved by that little rock. So, in other words, we're looking for h, okay? And there are two pieces of information it's given here. So we have the time of h being 1.25 seconds, and we know the time for h. We know the formula for it. We have it right there, okay? Let's see, where did we put that? Or maybe I can just copy this. Okay, maybe I can just copy that. Right here. Yeah, so I can copy this and bring it right down there. Okay, just because I want to use those formulas again. So the T of H is V0 sine alpha over G. V0 sine alpha over G. The T of H is V0 sine alpha over G. So 1.25 is V0, which we don't have, okay? Sine of alpha, which is sine of 73 degrees, over G, which is 9.81. So I can easily find V0 out of that, right? So V0 is 9.81, 1.25 over sine of 73. Okay, if you calculate that and put that in your calculator, you'll get 12.8 meters per second as your initial velocity. Okay, now what we're actually looking for is the height of that point, and I know the height of that point formula. I know the formula for it. The height is V0 squared sine squared over 2g. V0 squared sine squared over 2g. So I can easily find the height now, being height is V0 squared sine squared of theta over 2g. Okay, now we have V0, so 12.8 squared. We have sine of 73 degrees squared over 2 times 9.81, which is the g. Okay, now the next question is asking, how tall is the building? Okay, so in other words, we are now dealing with type 3 of these. See, because once it's going all the way down, all the way up, and then coming back to the launch point, now it is going down with a velocity of 12.8, but it's going down with a negative angle. In other words, if I want to draw it, I have to draw something like this. So that is the building. Okay. And velocity of 12.8 meters per second. And then what you have is It is going all the way, getting to this point, and then falling down to the ground, to G, okay? Now we're looking for this point in the range has the same type of velocity as 12.8 meters per second, but it is this time below theta at this point is negative, or it is theta of negative 73 degrees. It is positive, and there is negative. Okay, so let's find out the velocity along the initial velocity along the y direction. So along the y direction, v0 of y is v0 cosine of 73 degrees. Okay, so we have 12.8. It's actually sine. So here is we have sine, not cosine, we have sine. So sine of 73. So sine of 73. And if I calculate that, I will get 12.8 times 0.956. Okay, now if I put that in my calculator, I will get 12.8 times 0.956. I'll get 7.1. So 0.9 actually. So 12.8 times 0.95. 0.95. It is 12.16 meters above the ground is the height of the building. Part C is asking how far from the building does the rock land. So we have the initial velocity along the x direction, right? We have the initial velocity along the x direction. So part C, initial velocity along the x direction, v0 cosine alpha is 12.8 cosine alpha is cosine of 73. If I calculate that, I will have 12.8 times the 0.29, which is the cosine, 3.7. So I have 3.7 meters per second as my initial and constant speed along the x direction. The x direction, we have a constant speed no matter what, right? So now what we have also the time for it. So it's taking 6.13 seconds to hit the ground, 6.13 seconds to hit the ground to this point, okay? So I can just write a formula for x being vt, constant velocity. So x is velocity along the x direction, which is 3.7. The time was 6.13. And so what I have is 3.7 times 6.13, 22.6. So 22.6 meters away. All right, let's take a look at this problem, example number 9. Now, a marble is thrown horizontally with a speed of 15 meters per second from the top of a building. When it strikes the ground, the marble has a velocity that makes the angle of 65 degrees with the horizontal. So in other words, you know, we're giving you the final velocity angle with respect to x direction, which is 65 degrees below, okay? $65, so right there. And then from what height above the ground was the marble thrown in the air? Resistance is negligible. All right. So what we have is an object, okay, with being thrown with 15 meters per second from top of a building. When it strikes the ground, the marble has a velocity that makes an angle of 65 degrees with horizontal. In other words, okay, that's the point that is hitting the ground, and it is making an angle of 65 degrees above, below the ground. So this is the ground point, okay? So this is the ground, right? It's actually very easy. In other words, your theta is 65, initially is 65. And velocity is 15 meters per second, so you can find a velocity along x and along y, and solve the problem. Now, what we're looking for is from what height above the ground was the marble thrown in the air. In other words, we're looking to find the height of the building that this object was thrown, okay? We're looking for the height of the building, okay? So we're looking for the height that object was thrown. That's what we're looking for. Okay, work on it. If you have any questions, email me. I'm going to leave this problem to you. It is exactly the same as finding the height of the building, just like that. It's exactly the same as what we did. So try to solve it. If you have any questions, let me know, and we'll work on it. All right. So this is the end of chapter 4. I solved a couple of questions here, and so this will be an example type of video as well. And we'll continue for our work with the next chapter later on. All right. Let me know if you have any questions. I'll talk to you soon.